Okay, I'm just going to keep going with the webinar here. I think we had some technical issues with the broadcast, and I got started on this, so I don't know how much people got. So let me just back up really quick here. Remind you that there's information about the session on the ISOP study group webpage on the GitHub page. There's a vignette down here that I posted last night that'll take you through basically what we're going to go through today. So it's got all the code and the results. I'll run the code for the session today, and but it might be a little more pleasant to look at this document here. And the session is on using a PK/PD model for simulation-based assessment of probability of technical success in drug development. And I mentioned earlier that so I'm trying to frame this in terms of probability of technical success, but really the focus of the session here today is going to be doing like in a larger scale population simulation from a MRD solve from a model and MRD solve. So a population PK/PD type model and MRD solve, the type of work that we're going to do today and the simulations that we're going to do, they've got a lot of applications beyond or in addition to just probability of technical success. But I thought I'd frame the webinar today in terms of PTS here, just because it just seemed like an interesting point to bring up. And so I'll say a little bit about that background, but most of what we're going to be doing today is going to be focusing on the mechanics of doing larger scale population simulation with MRD solve. So I've got some references in the document here that you can read more about probability of technical success. And just by way of introduction here, so we're talking about quantitative decision making. So trying to make decisions in drug development, whether it's picking a dose to go forward with, or just trying to decide whether the compound can even go forward. And so when we're talking about probability of technical success, we're thinking about, okay, what is success? So does or could our compound achieve a sufficient response to either keep going, or does this dose sufficient to give us a high probability of being kind of successful? So we got to think about what is success, what is the metric that we want to use for success, and then what value of that metric, what value does that metric need to reach in order for us to have a success? And the probability piece in the probability of technical success kind of means that there's some level of uncertainty in the answer. So we don't know the truth precisely. We don't know exactly what's going on. There's some uncertainty in our estimates in the model, and so that it's less likely that this assessment is either going to be either yes or no, but we're going to have some level of uncertainty. So we want to quantify how certain we are about reaching that technical success. So this is just to get you oriented here. So this is a slide that Mark likes to show in some of his presentations. So talking about quantitative specification of decision criteria. So we're talking about all these different types of criteria. So effect size of 3 points, at least 90% of patients. We want to be 15% better than the competitor. So we're trying to take our drug development questions and make them quantitative. And so these are kind of some of the types of metrics and some of the types of criteria that we're talking about when we're talking about probability of technical success. Just to adapt some of the notation from the references we got here from Ken Kowalski, Jonathan French, Mike Smith, and I think it's a lot of the Pfizer pharmacometrics guys that kind of publish a lot of the references that I drew from for this webinar. They talk about this delta I, and so this delta is their measure of their treatment effect of interest. And this delta I can be calculated, and this is a function of omega, or theta, omega, and sigma. And this is basically going to be our population PK/PD model. So we've got our thetas, so those are fixed effects or our population parameters. Omega is that covariance matrix for subject level random effects, and the sigma is a covariance matrix for within. So it's our residual error model, and we can simulate from that model, and that's what this F of sigma, theta, omega, and sigma, and we can calculate this metric basically from that population model. Now, because we don't know these parameters exactly, this delta is a random variable. So the theta comes from a distribution, an uncertainty distribution The same thing with omega and sigma. And so we can draw from those uncertainty distributions. We can simulate from the PKPD model. We can simulate our change from baseline or a mean response, and we can get a distribution of these deltas. As we saw from that other slide, this delta I could be a lot of different things. It could be a mean response. It could be a mean change from baseline, median time to event, or it could be some relative measure. So say we've got a competitor and we want to be better, at least as good as a competitor, or maybe so much better than a competitor. So it could be a relative measure, comparing some kind of test and reference. I guess it's not treatment here, but some test and reference kind of case could be that delta as well. And to put this into this probability technical success formulation, so we want to calculate the probability that this delta is greater than some target value. That's our TV. And so that's the actual answer that we want to meet. And this calculation is based on whatever our current information is, our best knowledge of what theta, omega, and sigma are. And we get those from fitting the model to data. And as we progress in the drug development program, we get more and more data. We get more and more information about theta, omega, and sigma, and we maybe we'll have a more accurate answer, maybe even a more precise answer about what that probability that this metric is going to be greater than our target value is. And so the most of the work that we're going to do here today with MRG Solve is we're going to be taking a population model. We're going to be doing this, and we're going to be simulating this metric kind of repeatedly as a function of theta, omega, and sigma. And we'll show you how to ramp that up. And then there's just going to be some R coding here to calculate this probability. So we'll get this distribution of delta is what we're going to be simulating. Then the rest of it from then on is going to be some R coding to figure out kind of what the probability is that this delta is greater than our target value. You can keep following along in the vignette here, and I'm gonna switch over to the RStudio session and code some of this stuff up, or just kind of run some of this code and show you some of the intermediates here, and hopefully it'll be clear how what's kind of going on with these simulations. So we'll do the setup. I'm going to load MRG Solve and some other dplyr and some other packages. I've got some functions here that I'll share in this functions.r and try and point out where those are. There's an RNG kind, so I'm going to do the simulation. We're going to parallelize this with a parallel package, and to get that to be reproducible, so we can set a seed in R, and as long as we're using this Liqueur CMRG random number generator, that'll be reproducible, and I'm going to set this MC core. So right now I'm running on RStudio server, running on an Amazon web server instance. We're running 32 cores, and so this is going to parallelize the simulation across 32 cores. That's what the MC cores is, and I'll show you a couple other options for parallelizing if you're running on Windows and things like that. So let's first just look at a simulated a population that we want to simulate. So you'll see that the model's got some covariates in it. It's got BMI, it's got EGFR, it's got sex in the model, and I'll show you that in a minute. But first, I just want to read in this data set. And basically what I did is we took an NHANES data set and we simulated a new larger data set. There's a reference for doing that, and that's in JPP. Stacy Tannenbaum and Dan Mold and Nick Holford and Peck and Lee. They showed a way that you can take this data set and you can take one kind of multivariate distribution and you can simulate these continuous and categorical variables using this method here. And so I'll load this data set here, and we can look at it. These here, so we've got a bunch of weights, ages. We've got some stuff that's not in the model here: renal function stage, ALT, T-billy. But basically, we took so I went to NHANES website, downloaded the data sets, kind of put the data set together, and then I took that data set and I simulated a much larger data set so we can sample a lot more people in this. And so I'll take this NHANES data set and we're just going to filter it down. So RFST is at renal function stage. And so we'll get just either people with normal or mild renal dysfunction. And I'm going to limit this to ages greater than 18 or equal to 18. Also going to limit the BMI in here to be between 20 and 35. And then I'm going to just create another flag in here called BMIG. So this is BMI group, and I'm just going to artificially just create a group of people that are either greater than 25 or not greater than 25. And that's going to be BMIG, and that's going to be 1 if you're greater than 25 and 0 if you're not greater than 25. We can summarize this. So we've got, I'm just going to summarize it by renal function and then BMI group, and we've got this number of people in each group that we can sample from. So that's going to be our kind of population that we're going to be using to calculate this probability of technical success. I made a function here called GenData, and that's going to take in that. This might be a little bit gratuitous. Maybe we didn't need a function. I kind of had bigger plans for doing this for a bunch of different doses and things like that. But this will basically take that data. So we're going to take this, the NHANES data set, and we're going to pass it into this GenData, and I can ask for 1,000 patients here. That's the second argument N, and I'm just going to do one dose level here, 500 milligram dose, and I'm just going to call this is my set 1. Looking at this data set. So now we've got 1,000 people. They're all getting 500 milligram doses. The dosing here is going to be every 12 hours, and we're going to do 20 doses. And we've got our usual EVID and compartment here, and the first dose is going to be at time 0. But now you can see we've got a BMI, we've got an EGFR, sex for each patient here as well, and then some variables here to carry along in the data set. And all this function is going to do it's just pretty straightforward R coding. It's going to calculate the total number of people we need to simulate. It's going to take that that NHANES data set. It's going to select some columns that we're interested in. So these are the covariates. It's going to take a random sample from that really large data set, and we're going to renumber the IDs. Here we're going to create some doses here. And so this is just going to calculate, this is going to give me 1,000 people at each dose level. And this is going to fill in the every 12 hours and the total number of doses. Then we're just going to join together up the doses with the covariate information that's going to join by ID. And then we're just going to return that result. Certainly don't have to put this into a function. I had originally been making more data sets, and I kind of simplified this a little bit at the last minute and just decided to keep this function around. But we can take that NHANES data set and we can kind of filter for a BMI greater than 25 to make one more population to do the PTS calculation. Again, we're going to get 1,000 patients here at 500 milligram dose, and we're going to call this set 2. So set 1 is kind of all BMI takers between 20 and 35. Set 2 is just going to be people greater than 25. And I'll combine this into a single data set, and that we'll kind of simulate these at all kind of in one run, right? So, and then we'll kind of analyze them by the different data sets. And that'll just kind of give you a little bit of feel kind of for getting that population right. So we're going to do this probability of technical success, and we want to simulate a population that we think is going to be applicable for where we're going to do the study of this drug in a clinical population. And this is going to, and this kind of little exercise here is going to give us some idea for what the consequences are for having a different BMI distribution. I think we can take this and we can group by G, and we can summarize. we can see that the group with all takers, we got a mean BMI of 22, and then we've kind of skewed it quite a bit here for this other group here. Okay, so that's kind of like our simulation data set. So we've got this template we're going to simulate from. It's 1,000 people in each group, and we're all going to simulate. We're just going to look at this 500 milligram dose, and we've got the covariates here on the data set as well to run that population model. Okay, so let's get to the model. So I'm going to read in. So that this mread function is a function we have in MRG solve. I've got a population model here. This is my project directory. So there's a models directory where I've got popmodel.cpp. And then I'm just going to do a quick update here, and we're going to run the simulation out to 10 days. And we kind of did a little bit of this last time, but I'll just kind of refresh. So you can kind of see what's going on with this model in MRG solve by just typing this mod to the screen. We can see that there's 3 compartments: gut, central, and peripheral. So it's a 2-compartment PK model, and we've got some covariates here in the parameter list, and then the rest of the parameter list is a bunch of thetas. And I'll show you what that looks like and how I got that. In MRG solve, theta doesn't really mean anything specific unless outside of kind of where you use it. So if you're used to working in non-mem, theta means something special, and in MRG solve, it doesn't mean anything special. But I've just parameterized this model in terms of theta because I knew that non-mem was using theta, and that when we go into non-mem to get the stuff, to get the estimates and things like that, non-mem is going to call them theta. So I'm just going to call my model theta too, just so that these names match up, and that's going to be key to doing this simulation. Just looking at the model specification file for doing this for this population model. So I've kind of included in the parameter list, I've included all my covariates: weight, sex, EGFR, BMI. And then I've got this $theta block, and I can't remember if we talked about this before, but $theta is just a quick way to get parameters into the parameter list. So if I look at the parameter list, I've got everything in param, and then I can just specify $theta, and I can just give the values. So I don't need to worry about the names. And MRG solve will name these things. So it'll name the third thing here. It'll name that to be theta 3. So theta 3 is 4.34. So the third element here in $theta is 4.34, and then I get that to be theta 3. And this is just a kind of convenience way. When you know your model's coming from non-mem, you can just kind of hack these in, and it'll save you a little bit of typing. Otherwise, we could just as easily have done something like this: theta 20 equals whatever. We could code that into the parameter list there. It's a little bit more convenient to code it into this theta block. We've got the compartments here: gut, central, peripheral. That's $CMT. And $main is where we do all the covariate modeling and where we incorporate the random effects. Again, when we create new variables, we want to prefix. We usually want to make them double precision variables. But I'll just trying to copy this covariate model, kind of similar to the way I had it in non-mem. We had to do a couple different changes here. We need to put semicolons at the end. We need to declare variables in MRG solve. But hopefully a lot of this looks kind of similar to maybe what you're doing in non-mem. So we've got the PK parameters here. We've got some random effects that we've derived in $main. And again, if you're thinking in terms of non-mem, this is like your $PK. We've got a single omega block for all 4 etas. We've got a sigma block for the residual error variates. We've got $ODE, where we just got a regular 2-compartment model. I set a $global. This is where you can declare global variables, where I've got a baseline value. So I'm going to use this I'm going to use this model to calculate the change from baseline. So I'm going to track this baseline value, and we've got some C++ coding here that'll let us define. So I can define CT. So that's the concentration in the tissue to be perif divided by VP. CP is cent divided by VC. And these are just preprocessor directives that will kind of substitute kind of this thing, cent divided by VC, whenever it finds a CP here. And that's a little kind of trick that you can use when you're coding in C++. In the dollar table, I'm going to derive my DV. So in here, this DV is going to be kind of like my PKDV. So that's going to be the plasma concentration with the residual error variant on it. And then I can derive some other variables. I don't think I need this IPRED, but I'm going to use in this dollar table, I'm going to derive this effect. So this is just a direct effect model. Maybe it's not that realistic, but it's what we got here. And so this is my effect. So it's going to be, I'm going to calculate it based on the driver, which is the plasma concentration. We're going to calculate this effect with some baseline effect. There's an Emax and an EC50 here. And this is going to get calculated at each record. And here I'm going to calculate the change from baseline. So if the new individual flag is less than or equal to 1, I'm going to set this baseline value, and it's going to be the effect. And I'm going to have two of baseline effects, one that either with the random the residual error variant on there, and then one without. So capital is without, lowercase is with. And then I'm going to derive the corresponding change from baseline. So it's the effect minus the baseline. Then it either it does or doesn't have the random error, the residual error on it there. And then I'm going to capture the only one we're interested in here is this lowercase DEFF, and that's the change from baseline with all the residual error in it. And so we're gonna request that variable to come out of the simulation run. So that's a model really quick. We won't kind of go through the non-mem model because it's going to look a lot like that. And you can just kind of imagine just a 2-compartment model with a direct effect PD model on it. And I'll certainly share this with you in the materials and look at it. I fit the model in non-mem with method equals Bayes. So we did MCMC Bayesian estimation. And when you do that, when you go into this, so the run number is 1001, and we've got this .ext file. Here I filtered down to get iteration greater than 0. When you do that, you get each sample from the posterior. So I think I just ran 1,000 samples here. But for each iteration, you get a draw from the posterior. And so we've got 1,000 theta 1s, 1,000 theta 2s, etc. If you're not running MCMC Bayes, you could maybe bootstrap your data set, and you could get a data frame like this where instead of iteration, this is the bootstrap number. So you could bootstrap the model 1,000 times and get something similar to this. And if we have time, I don't know if we'll have time now at the end of the presentation, but I'll show you a way that if you don't bootstrap the data set, but if you get the covariance matrix of the estimate, that you can simulate this, and we'll show you how to simulate this if you're running like a FOCE. But I'm just going to I'm going to do this calculation from the posterior from an MCMC Bayes run. I'm just going to randomly sample 500 iterations. Now the post is down to 500 here. And again, we've got thetas here, we've got some omegas, and we've got the sigma here. And so we can go to just any row here to get the set of thetas, right? So I can draw here and I can get a different set of thetas just by going to either row 5, row 6. I can get a different set of thetas. Go to row 9, I got a different set of thetas, etc. But to get the omegas, this isn't quite right. So if we want to pass in an omega matrix into MRDSol, we have to have it as an R matrix. So I'm going to use this function called asBmat, and that stands for as block matrix. And when I pass in this post, asBmat, what it does is it's going to look for columns that has capital omega in it, and it's going to scrape those columns, and it's going to generate matrices for you, and I can do that for the omega matrix, and I'm going to do that for the sigma matrices. And what this as BMAT returns it returns a list, and it returns a list of matrices. And so I can look at that first one, and I can look at the 100th omega matrix, and so I've got a list of 500 omega matrices here, and I can pick which one I want by looking into a different position in that list. And the same thing with sigma. I can look at the 100th sigma matrix is like that, and that's slightly different than the 200th sigma matrix, although not by very much. So that sigma is kind of much more. It's much more precisely estimated than the omega was, I think. So now we've got the three data items that we need to run the simulation. We've got the post, which is going to have our thetas in it. We've got our omegas, and we've got our sigmas. And just to point us back to here, so this is where we're at here, right? So we can draw from the posterior to get theta, omega, and sigma, and we're going to turn the crank to calculate our delta here to start to do that probability of technical success calculation. I'm going to do this in a function. I usually don't start doing it in a function, but once I get down the road, I usually don't regret functionalizing it. And I'm going to call the sim, and the sim function is going to take it in I. So that's the ith iteration. So we're going to do this repeatedly. And so I is the index of the iteration we're on. I'm going to pass in the posterior, so that post. And then I'm going to pass in that data set that we generated. That was that NHANES data set that we turned into a kind of like an MRG solve data set. I've got a little indicator here whether we want to do population simulation. I think in this one, we're always going to do that. And if we are going to do population simulation, what it's going to do, it's going to take the model object that we created. It's going to update with the ith omega matrix, and it's going to set that to omega through this OMAT function. And then it's going to update for the ith sigma matrix, and it's going to set the sigma matrix with this SMAT function. Remember, the model object just has kind of nothing in there now, or it's got zeros. And so if we're going to do a population simulation, we want to populate that in, and we can do it with the syntax like this. And then this is just the same kind of workflow that I had showed at the last study group session. So we're going to take the model object. We're going to say we want to use this data set. We're going to slice off the ith row from the posterior. So just to see what this looks like. So when we slice the ith row from the posterior, we're just going to get one set of thetas. Because theta 1 through theta 15 were in the model, it's going to update the model. So it's going to update the values of those parameters. So it'll be that current draw from the posterior. We're going to request this change from baseline, DEFF. And then we're going to carry out some variables. Remember, the carry out just copied some columns from the data set, and it's going to copy it from our input data set into the output data set. And so we think we're going to want to summarize by these variables here. And so we're just going to carry them out into the output. We're going to simulate. We're going to do a data reduction step here. So I think we're only simulating just probably the time 0 and the day 10 time here. But I'm going to filter that down so that we just get the day 10 time here. And so this will return just one observation per person. So everyone's going to have a day 10 observation, and we're going to boil this simulation down to be just one per person. Then I'm going to finally mutate. So I'm going to capture that replicate number so that we can summarize by replicate. So I'll set a seed, and I'm just going to run this. I can just test this simulation function. So I'm going to do the 11th draw there, pass in the post and the data, and make sure we do population simulation. And this is what the output looks like. So we've got 2,000 people, some in set 1, and then some in set 2. They're all at day 10, and then we've got that change from baseline output right here, and then we've got the replicate. These are all replicate 11. Just because we just did one replicate there. So we can ramp that up, set a seed again, and we can do 320 replicates here. I'm going to fire this off. We use MCL apply, and that's a parallelization scheme that you can use either on Mac or Unix. And that's this multi-core lapply. So it's like lapply, except it's going to take these jobs. It's going to split it across. We've got 32 cores running now. And it's going to basically call this simulation function. Then we're going to pass in the arguments here. We need to pass in the posterior. We need to pass in that template data set. We need to make sure that we're doing population simulation. And this is going to return a list of data sets. And we're just going to take that right out of that MCL apply, and we're going to bind it into one. We're going to use bind rows out of that dplyr package to bind it into one single data set. So that we just came in just under 40 seconds there. And again, that was kind of highly parallelized. We had 32 cores going, but that got us 640,000 kind of patient replicates, right? We had 2,000 patients in each data set. We did 320 replicates, and that got us 640,000 kind of patient replicates out of there. Just to count this a little bit. So again, so everybody had the 500 milligram dose. In that set 2, everybody's in that BMI group 1. So greater than 25, and then set 1, again, they were kind of split between BMI group 1 and 0. I don't think we're gonna have time to go through this now, but I gave you a couple other ways to parallelize this. So if you have access to Sudden Grid Engine, Metro Research Group maintains a package called QApply, and that basically does the similar thing to what MCL apply does, except it just takes the jobs and it sends it out and schedules them on Sudden Grid Engine. So if you've got jobs that take like an hour to complete, you might parallelize this using QApply. I've got some of the syntax here. I'm not going to run it in the interest of time, but it'll split all those jobs up, and it'll schedule them on Grid Engine, and it'll send you back another list of all the simulated data and bind it up again. You got a little different way to pass the arguments to that function, but it's the same kind of concept here. And this is really great when you've got a really, really big simulation. So when the simulations take hours or a day to do, you can parallelize this, and it's really efficient. There's just more overhead here because we're scheduling this through Sun Grid Engine than what it takes to do MCL apply. And then if you're working on Windows, I've got one example here using Do Parallel, and I don't usually use this package. I almost always use MCL apply. But if you are running Windows, this will do a setup that I think will get you the same thing. I don't know all the options here, so there might be a more or less efficient way to do that with a Do Parallel package. But this works, and it seems like it gives me the same thing that MCL apply is doing. So you can use Do Parallel on Windows, and it'll also work on Unix and Mac too. So there's a couple different ways to parallelize that simulation, and I'll kind of see how we're doing on time here, but I wanted to take those, and I can go back and show you some of these if there's some interest. Otherwise, it'll be in the vignette for you to play around with. But I'm going to take that output now, and we're going to calculate this probability of technical success. And that's just a summary. That's just a summary that we do from the simulated data. From here on out, this is just regular R coding, and you might have a different way of coding this up. I'm going to use this dplyr package to summarize this, but you might have a way that's more comfortable for you, and that's fine to do. But there's really nothing after this point that's specific to MRG Solve or anything like that. It's just however you can get these summarized would be fine. And so I'm going to take, so we're talking about change from baseline, and you can see our values are anywhere. We got a -11 here, we got a -45, and I'm going to just take, I'm going to do one summary here where we're going to try and calculate this fraction of patients reaching a target value. And so I've got kind of an optimum target value. of 25-point change from baseline, and then I've got, or this is my kind of optimal. So this is going to be harder to reach. And then I've got this minimal target. I say, well, I want it to be at least 22, and it would be great if it was 25. And so we're going to calculate that fraction of patients reaching this kind of optimal target and this minimal target here with this L-apply loop. And basically, it's just going to take our simulations. We're going to group by the replicate, by the dose. So there's just one dose, but I want to get that in the output too, and then the set. So that I got these two different populations in this data set. So we're going to group it by those, and we're going to summarize, and we're going to look at what fraction of the kind of patient replicates had a change from baseline that were less than this target value here. And so this is going to be logical. And when you take the mean of a logical, it's the fraction of them of that kind of vector that where it comes out to be true. And so this is going to be that fraction. And so that we're going to boil this down to a fraction, and we're going to kind of tack on that target value here so we can plot by that target value as well. And then we're going to, this is just this little mutate on the end here that just turns it into a factor that I'm going to use for plotting too. But I can look at the sum. And so now I've got, for each replicate, we've got set 1 and set 2, and we've got a fraction calculated at the given target value. So these are the 25s, minus 25s, and then there's going to be minus 22s at the end here. But this is basically like we had 320 replicates times 2, 640, and yeah, and then this is times 2 different cuts. Oops, times 2. That's where we get that 1280. So we got basically one replicate at each of 2 cuts, and then 2 different data sets there. I'm going to just take this summary, and I'm going to just calculate the density on it because I wanted to make this plot here. And we're going to look for this target fraction. I'll show you what this density does. That density function, it just calculates for each dose and kind of value here. It calculates the X value and the Y, and I'll show you what this plot looks like. But we want this target fraction, and I said, okay, we want to get at least 65% of the people kind of greater than this target value here. And I'm going to plot this out, and this is why I did this density business, is that we can make a plot of this, of the distribution of this fraction with response greater than this target value. And so this is the distribution of that fraction, and it's either at the kind of the optimal target, so the minus 25, or that minimal target, minus 22. And then we've got the set 1 on the top, and we got the set 2 on the bottom. Basically, I've shaded in the area where we're greater than 65. So I kind of put a line here at 65%. And the shaded area, and that's the, if we kind of integrate that in that total area, so that's going to be the probability that we're greater than 65% for either at this optimal cut or this kind of more minimal cut. You can see we've got a bigger area for that easier target here, kind of assuming that we always want to get 65% of the people kind of, or we want to get more than 65% of the people with that response. So it's easier to get this this minimal cut rather than this optimal one. And then looking at the top, comparing the top and the bottom, now we can see that the people in this data set 2, we've got a smaller area here. So we got people with bigger BMIs, and we've got a smaller probability that we're going to get more than 65% of the people kind of greater than these cutoff values. And so I simulated in a covariate effect in there in the model that you can kind of look at and kind of see how that's working. And so I'm going to take this summary here, and I can just take the summary data, and I'm going to group it by the set and the typical value here, and then the dose, and then I'm going to calculate this probability of technical success, and that's just going to be the fraction where that fraction is greater than the target fraction. So that's really just this. We're just trying to get the area of this density where we're greater than our target. And you can see for here, it was about 50-50 for this one here, and then we had a much higher one for that lower target for the 22. There we've got only 9% where in that lower tail where we aren't hitting that target, and then it gets harder when in that set 2 with a higher BMI. So here we've only got 19% here, and then we've got 75% in this upper tail here with that second data set. And I think that maybe there's an unrealistic covariate effect in there related to BMI, but that's just kind of what it is. And the point here is that this probability of technical success, it's this tail area where we've got, let me just go back to here. So we want this probability that delta is greater than that TV. And so we're looking, this is that tail area here that we're showing here. And then we can boil it down to a probability number by just counting the number of replicates where this fraction was greater than that target value. I'll do another summary here. So this is the mean. So we can kind of, maybe we're not thinking about fraction of patients. Maybe we just want a mean response greater than some target value. And again, we can take our simulated output. We're going to group it by replicate, dose, and the set. We're just going to calculate this mean change from baseline. And here I'm going to have a target value. It's going to be, we're just going to change it up here. It's going to be either minus 28 point change from baseline or 26. Do this density calculation and just to show this plot here. Now things are looking a little bit rosier. Now we want to be, right, we want to be more negative than either 28 or we want to be more negative than 26. And again, this kind of this minimal target, we kind of see more of the area shaded here than this optimal target. And then the set 1, we've got a higher, more area here where we're kind of exceeding our target compared to set 2. But again, this we want to kind of see what this shaded area is here. That's our probability of technical success. We can take that summary, and then we can just count the number of replicates here where the mean was less than our target value here. And so we can see for that 28 in group 1, that was 72% where we were successful, and then just under 30% where we were not successful. And then if you compare that to group 2, we're just kind of 40% probability of technical success down here. And then that easier target, it's rosier picture, so we kind of had a high probability that we were going to meet this 26 point change from baseline, 92% here, and then the same thing for that second population. But it was only 80%. And so part of doing this is kind of calibrating how comfortable you are, kind of how sure do you want to be that you're going to reach this target. So maybe 70% is good enough, or maybe you don't feel comfortable with that, or you want to do 90%. Or maybe if you think you want to reach a 28 point change from baseline, and if you think you're going to have this higher BMI group, maybe you're not comfortable with 41%. Maybe you want to see that higher, and so you might kind of reassess things about where you want to be with a compound. Okay, so we're just getting to the end of the hour here. I apologize. We had the technical issues at the beginning of the hour, but that basically ran through the calculations that we needed to do to calculate probability of technical success from a population PK/PD model and non-mem. The last section here, I'll just leave it for a discussion item. Maybe a lot of people aren't running Bayesian analysis for their PK/PD modeling. And so section 8 here is just, I'm using the SimParp function, and that comes out of the MetroMarG package. And that'll just show you a way to take, if you do your modeling in non-mem or I guess any other package, and you can get that covariance matrix of the estimate. And this will just show you how to simulate your thetas. It'll show you how to simulate omega matrices, and it'll show you how to simulate your sigma matrices under kind of some distributional assumption. So the thetas are multivariate normal, and the matrices are inverse Wishart. But it'll basically get you something similar to what you get out if you bootstrap the data set or if you did Bayesian analysis. And this just shows you how to do that. Then it'll show you a little bit about how to I have one little piece down here on how to explore how your the simulated random effect variances depend on the degrees of freedom. So when you do that SimPar, when you simulate from an inverse Wishart distribution, you need to say what those degrees of freedom are. And I've set them here. So I've got a degrees of freedom for omega and for sigma. And I just do a little bit of a sensitivity analysis to show how that those omegas that get simulated, how they depend on the degrees of freedom. Okay, thanks everyone for attending the session today. I apologize again for the technical issues. We'll have the vignette here that we went through today is already posted on the GitHub page, and I'll there's some more stuff that I need to pull together here to make this doable for you guys, and so give me a little bit of time, but we'll get this posted up on the GitHub site so that you can get access to that model, or at least to the posterior. We'll at least post the posterior there so that you can run some of these simulations. Thanks again for coming. I'm just going to stop the broadcast now, and please post any questions you have to the Discuss forum, and I'll try and respond to the questions as best I can throughout the day today. Okay, take care. Thank you, everybody.